Hello and welcome to my chemistry lesson. Today I'm going to do a lesson on GCSE chemistry, atomic structure of the elements. Just going to share my screen with you, so if you give me 1 second. Okay, so you should be able to see my screen now. And like I said, this is a GCSE chemistry lesson on the atomic structure of the elements. So, prior knowledge, what you should know from from Key Stage 3 chemistry, that's years 7, 8 and 9. Describe the terms atoms, molecules, compounds and elements. Recall and describe the particle model of matter for solids, liquids and gases. And finally, you should be able to describe and explain, to an extent, the properties of the different states of matter using the particle model. So, what we're looking for, by the end of this lesson, you should be able to describe the general atomic structure using the subatomic particles and their characteristics. You should be able to explain how to calculate the number of subatomic particles per element using information from the periodic table with examples. And finally, you should be able to explain how to determine the electronic structure of an atom using the periodic table to a very simplified extent. So let's just quickly recap the particle model of matter. You've all been taught that all materials are made of particles. In fact, all substances are made of particles called atoms. They are really, really tiny, teeny tiny, too small even to see with the most powerful of microscopes. Every element known to humankind is made of atoms. It's the differences in the structure of the atoms that make up the different elements. So, atomic structure, the actual structure inside the atom. What we've got here is a 3D model of what we expect to see inside an atom. This is the nucleus. It's the central part of the atom. It contains particles called protons and neutrons, and they're the only things in the center in the nucleus. It has a positive charge overall because the protons are positively charged. Neutrons have zero charge. That means that that central region of the atom has a positive charge overall. Almost all of the mass of the atom is concentrated here because protons and neutrons are heavy. Relative to the rest of the atom, the nucleus is teeny tiny. That means that that nucleus in the middle, even though it looks quite large in comparison, is actually the smallest proportion of the atom. Mostly the atom is made up of empty space. The electrons themselves then. Electrons move around the nucleus in electron shells, or what we call orbitals. They're negatively charged. They have the opposite charge to the nucleus. And it's this negative charge being attracted to the positive charge that prevents the electrons from just careening off and away from the atom. They are tiny. They're very, very small in comparison to the atom's nucleus, in comparison to the protons and neutrons, but their shells cover a lot of space inside the atom. The size of their shells determines the size of the atom. This means that as you get heavier and heavier atoms, they have more and more shells, and to fit those shells in, each shell that comes after the last one gets bigger and bigger. So the more shells, the bigger the atomic radius, the bigger the atom. Electrons have tiny, tiny masses. It's literally so small that we usually call it a GCSE 0 or negligible, meaning that we ignore it for all intents and purposes. The other way of thinking about this is as above, so below. It's a bit like the solar system model, where the nucleus would represent the sun, the biggest part of our solar system, the biggest star in the center of it. And the electrons would be represented by the planets, and their orbitals would be the path they take around the sun. But if you think of it, the solar system is a huge, huge region of space. The sun is in the middle, and it's smaller compared to everything else, but it's bigger than the planets, which are rotating around it in orbitals. Everything in between that is just empty space. It's another way of thinking of it. So, all atoms are made of the 3 subatomic particles, and each of these particles has their own properties, which are summed up in a table that I've put together. So we take a look at the first one, particle proton. It has a relative mass of 1. Now, relative mass means its mass relative to a proton. It doesn't have any units, or if we do use units, we tend to say AU or atomic units, but the proton has a relative mass of 1 and a relative charge of +1. It's located in the nucleus. The neutron is also located in the nucleus. It is the same mass as a proton. It has a relative mass of 1, but its charge is 0. It's neutral, electrically neutral. That means that the proton and neutrons that are gathered in the nucleus have an overall positive charge for that nucleus. Finally, the electron, which has a tiny relative mass. It's tiny in comparison to the protons and neutrons. They have a mass of 1. The electron has a mass of 0.0005, or 1 divided by 1,838 approximately. Its relative charge is -1. It is negative compared to the proton and the neutron. And its location in the atom is in the orbitals, or the shells, that are outside the nucleus. There are no electrons inside the nucleus. So that's the description of general atomic structure using the subatomic particles and their characteristics. 3 particles, proton, neutron, electron, characteristics being their mass, their charge, and their location. Using that now, explain how to calculate the number of subatomic particles per element atom using information from the periodic table with examples. So, to calculate the numbers of protons, neutrons, and electrons, we do need a periodic table. Lots of pupils tend to think that this periodic table is just there, but actually it's got a load of information in it. When you come to your exams and you're sat there, you get a periodic table in your chemistry or your combined science chemistry exam. And what you'll find is that that can be annotated. When you're sat there in the exam, you can write things on it yourself. And if you can remember some of the things that you need, then it makes life a lot easier. For example, the key. This key is really, really useful for telling us what the arrangement of our table is. So that key there tells me that the relative atomic mass is the number on the top. The atomic symbol is the letter. The name of the element is printed under that. And the atomic, or the proton number, is at the bottom of the box. So if I take hydrogen as an example, and I take this bit here, then that is my relative atomic mass. That is my atomic symbol. That is the name. And that is the proton number. So, the modern periodic table is not arranged by mass, but by the atomic or proton number. This means that going from left to right, from top going down to the bottom, the proton number on the bottom goes up by 1 every time. So hydrogen, bottom number 1, helium, bottom number 2. Then we go down a row, lithium 3, beryllium 4, boron 5, carbon 6. As we're going along, the proton number increases by 1. Relative atomic mass number, the number on the top, tells us both the number of protons present and neutrons present in the nucleus. It doesn't allow us to work out how many of each one. It just tells us that there is a total number of 11, for example, with boron, protons and neutrons in its nucleus. But the bottom number, the atomic number or proton number, that just tells us the number of protons present in the nucleus of the atom. So at this point, I've got 11 particles in the nucleus, 5 of which are protons. So far, so good. Let's use hydrogen as an example. It's the simplest element in the periodic table. It has a relative atomic mass number, and I use my key to identify that that here is my relative atomic mass number, and it's 1. It also has an atomic or proton number, and again, I can use my key to identify that that is also 1. So in this hydrogen atom, I have one thing in the nucleus, and that one thing is a proton. The atomic number tells us hydrogen has 1 proton in its nucleus. The mass tells us that there's only that proton. There are no neutrons because a proton has a mass of 1. This did also tell us that there is 1 electron, but where did that information come from? Well, let's take another look. I call this the pen method. You may have been taught something similar by your teacher in school. You may have seen something on the internet, but to calculate the proton number, dead easy. Atomic or proton number of the element. That's my P part for my pen method. To calculate the electron number, and this is only for an atom, not an ion, which is a charged particle, but the electron number for an atom is always the same as the number of protons. So for hydrogen, I had a proton number of 1. For the hydrogen atom, I have 1 electron because it matches the proton number. This keeps the charge electrically neutral overall. To calculate the neutron number, well, actually, that's not too difficult when you think about it, because if the atomic mass number is the number of protons and neutrons, and then someone tells me the proton number, then the difference is the neutron number. So to calculate neutron number, subtract the proton number from the atomic mass number. Let's take a look at some examples. First one, let's say lithium. So I have a proton number, my bottom number there, according to my key, which is 3, meaning I must have 3 protons in that nucleus. That also means that because this is an atom and overall has no charge, the number of protons must equal the number of electrons, so positives cancel out negatives, so electron number must be 3. To find the neutrons then, I take the 3 protons away from the 7 atomic units in the nucleus. That leaves me with a mass of 4, which must be the neutrons. Let's try that with a different one. Boron has a proton number of 5, because 5 is the bottom number, and it corresponds to atomic or proton number according to my key. The electrons then have to equal 5, because protons and electrons are the same. And the neutrons, well, to find that out, I take the 5 protons away from the 11 mass in the nucleus, from the atomic mass number, and it leaves me with 6 overall, so I have 6 neutrons. Another example, neon has a proton number of 10, so the electrons must be 10, and the neutrons are the atomic mass number, 20, take away the proton number, 10, which leaves me with 10. Last example, and this one's a bit of a weird one, but it does happen sometimes. It will ask you about chlorine. As you can see, chlorine has a non-whole number mass, which can happen. This is due to something called isotopes, which we're not going to go into this lesson. But it doesn't matter if it's a non-whole number mass, you do exactly the same thing to work it out. So proton number is 17, because that's my proton number according to my key. The electrons must also equal 17, because that's protons equals electrons in the atom. The mass number is 35.5, take away 17, that means I must have 18.5 neutrons. And even though you're probably thinking, how do I have half a neutron? In this case at GCSE, that is the correct answer, and you don't need to look too deeply into it. So that then is explain how to calculate the number of subatomic particles per element atom using information from the periodic table with examples. The last bit, explain how to determine the electronic structure of an atom using the periodic table. Let's get on to that now then. The electronic configuration. When discussing protons and neutrons, it's easy to say where they are because they're always found in the nucleus of the atom. So we don't actually have to say anything about anything. If someone says, right, you've got 12 protons, where are they? They're in the nucleus. You've got 15 neutrons, where are they? They're in the nucleus. Oh, good. But the electrons, they can have different locations based on how many of them there are around the atom. And we can address this, we can give them a kind of address system, a bit like we have addresses for our houses. And we call this addressing system the electronic configuration. The electrons are found in shells. What if there's more than one shell? How many would there be in each? Why? How do we know? Again, we can assign an electron to specific shells in the atom if we know or follow the rules for it. And again, we need the periodic table to do this. So let's take a good look. Now, even though this looks like the slide before, I've actually changed the bit at the top and I invite you to read it with me. The modern periodic table is arranged in columns called groups and rows called periods. You can see at the top there are numbers 1, 2, 3, 4, 5, 6, 7 and 0. Those numbers are the group numbers for the column underneath it. So for example, group 7 is fluorine, chlorine, bromine, iodine and aspartame. The periods are the numbers of the rows. They're not present on this periodic table, but the first row, hydrogen, helium, is period 1. The second row, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, that's the second period, second row. So what we've got here then is elements in a column or group. And that actually means that they have the same number of electrons in their last or their outer shell. You always call it an outer shell. Never use the plural. I've seen it done so many times where people throw outer shells. Actually, you can't have outer shells because as soon as you have an outer shell, it's the last one. You can't have more than one. Elements in a row or period have the same number of electron shells. So, for example, fluorine, chlorine, bromine, iodine, astatine, they're in the same column, so every last shell of theirs has 7 electrons because they're in group 7. But fluorine has 2 shells, chlorine has 3 shells, bromine has 4 shells, iodine, and so on. And this is because as you go down a level, you increase the number of shells. Group number of the element tells you how many electrons there are in the outer shell of that group. For example, all of group 7 elements have 7 electrons in their outer shell. Group 6 then would have 6 in their outer shell, and so on. The period of the element tells you how many shells it has altogether. For example, period 1 elements only have 1 shell. Period 2 have 2 shells, and so on. It is important to remember though, when we move from period 1 to period 2, e.g. shell 1 to shell 2, we have to fill shell 1 completely with electrons. This means that we can say the shells before the period that we're finishing on are completely full. So what are the rules for it then? Well, we can use this relationship between group number and period number to help determine the electronic structure of an atom. The first period has only 2 elements, hydrogen and helium, in it. This means there's only a maximum of 2 electrons in the first shell. In other words, shell 1 can hold 2 electrons, maximum, full stop. For period 2 and 3, there are 8 elements from left to right in each period. If you count them from lithium to neon, or from sodium across to argon, we'll see there are 8 elements there. That means that the second shell and the third shell can each hold a maximum of up to 8 electrons. Now at GCSE, we don't study beyond calcium in period 4. We don't go into the transition metal elements unless you're studying separate chemistry, and even then we don't go into too much detail with them. So because of this, we stop in period 4 at calcium, and so we say that shell 4 can hold up to 2 electrons. It's a bit of a fudge because when you get to A level and if you decide to take chemistry as a degree, you'll find out differences, but it's just what it is for GCSE. Now we can draw these electronic structures or we can just use numbers to describe them, but these rules are important and we have to know them. Shell 1 holds 2, shell 2, 3 hold 8, shell 4 hold 2. If you like, it's palindromic from top to bottom. A couple of examples then. Lithium. Now, lithium's got group 1. So the number of electrons in the outer shell must be 1. It's in period 2, so there are 2 shells in its atom, and we said earlier that the first shell must be full. All the shells below must be full. So the electron configuration is 2, because the first shell is full and the first shell holds 2. 1, because we're in group 1. And if we draw a diagram, then we draw the electron shells. You can see I've got 2 electrons on my first. Chlorine, a bit more complicated. Now I've moved down a period into period 3, which means that technically now I have 3 shells. But chlorine's group 7. Electrons in the outer shell then must equal 7, so the last shell has 7 electrons in it, and every shell before that must be full. Because it's in period 3, I draw 3 shells. I put 7 in the third shell, and I fill the other 2 shells according to my rules. 3 shells in its atom, so the first shell holds 2 and it must be full because I'm on the third shell. Second shell can hold 8 and it must be full because I'm on the third shell. And Mr. Johnson's made a mistake there because that should be 287, not 281. The third shell should hold 7, so the electron configuration is 287. And this is what it looked like as a diagram. Now I've used yellow spot or yellow circles to represent the electrons, but you can see on the first shell there are 2. The second shell, there are 1, 2, 3, 4. Third shell, 1, 4, 5, 6. And that is how to explain or determine the electronic structure of an atom using the periodic table. Once again, I want to say thank you very much for watching, and I hope you have a good day. Take care of yourselves. Bye-bye.